we continue our session, and our first speaker is Evgeny Sevost'yanov with the talk on the Koebe-Bloch theorem for mapping with inverse Poletsky inequality. Please, we see.
Dear organizers, dear participants, thank you very much for the organization of this conference and the possibility to make our reports here today. So the report is devoted to some analog of the well-known Koebe theorem. What is a theorem of Koebe? If we have a sufficiently good class of mappings, of the plane mappings, which are conformal, origin maps onto the origin, and f prime from the origin equals to 1. So for this class of mappings, this is the so-called S class. We have always that the image of the pole of the unit disk on the plane contains the ball centered at the origin of the radius 1, 4. So we obtained this result for more general classes of mappings, not always on the plane, but in the space as well. And this report is devoted to this situation of more general mappings. Here we give some notions and definitions used below. Firstly, we consider the vector functions f, which is defined by the equality 1. X is a vector which contains n components, n bigger, equal or bigger than 2, and f also is a vector function, as I said above. This transformation is supposed to be continuous. Always. Here we see on the picture a domain D, which is a connected open set in Rn, and the image of the domain D under the mapping F. Recall that a path is a continuous mapping of the segment or an interval in Rn. The length of a path gamma is defined as a supremum of such sums where the supremum is taken over all partitions by points of the segment AB. We say that a function rho, which is a Borel function, so the primage of any Borel set is Borel set as well. A function rho is called admissible for a path family gamma big if the relation 2 holds for every locally rectifiable path gamma small from the family gamma big. A path family is a set of paths, some set of paths. The notion of the modulus of families of paths is very important in the mapping theory. Let P bigger or equals than 1, then by the P modulus, we call the quantity which is defined by the equality 3, where the infimum is taken over all functions, all admissible functions of gamma, which are defined as above in 2. P modulus is the alpha measure on the path families. So what is the outer measure? This is the quantity which is equals to 0 for the empty family, which is the monotone function with respect to the inclusion of families of paths, and also the property of subadditivity holds for unions of families of paths for MP gamma. Given sets E and F in D, we define by the triple gamma EFD the family of all paths joining these sets in D, as in the picture you see. Here we give some definitions of the ball, of the sphere and of the ring centered at the point x0 and of the corresponding radii. Let us to give some definition. Let F be a mapping of a domain D in Rn, and let Q big be a Lebesgue measurable function which may be supposed equals to 0 outside of F from D. Let gamma indexed F of y0 R1 R2 denotes the family of all paths, the images of which under the mapping F joining the spheres in the ring of the corresponding radii. We say that F satisfies the inverse Poletsky inequality at the point y0 if the relation 5 holds for any Lebesgue measurable non-negative functions eta satisfying 6. What does it mean, this definition, 5 and 6? If we have a domain D, we see in this domain the prime image of all paths joining the spheres in the image and the mapping F. So gamma F y0 R1 R2 denotes this family that under mapping F maps on the right good family joining the spheres of the corresponding radii. This construction is applicable for many known classes of mappings. For instance, for quasi-regular mappings, we always have this relation 5 and 6 as well, or this function q, which is equals k multiply n, where n is the multiplicity function. In particular, we may show that the non-conformal mappings on the plane always satisfy 5 with q equals to 1. Also, we have the known fact about that this relation 5 maybe holds for more general classes of mappings, say for Sobolev classes. W1 and log, there are Sobolev mappings, so there are mappings having all first generalized Sobolev derivatives, which are locally integrable in the degree n, where n is the dimension of the space. If some quantity, which is called outer dilatation, is locally integrable in n-1 degree, then we may show that 5 holds for such mappings with some difficult function q, which you can see here on the picture, on the slide. These facts are proved by Marty Rickman Vyasila for quasi-regular mappings, and my teacher Rizanov with co-authors have proved this more general fact for Sobolev classes and more general mappings with finite length distortion, for example, in particular. This is a formulation of the known Koebe theorem from which I have started this report today. And what is about more general classes for Koebe in the context of the Koebe theorem? There are many results on this topic. Our results may be given below. Recall that a mapping F is a discrete if the prime image of any point consists of only isolated points, which may tend to the boundary of D, of course. Also, F is called open is F preserves openness of the set. Here we see some pictures on this topic. In particular, the item A describes the openness, so we have open A, and F from A may be also open with respect in the topology of Rn. The discreteness may be described as follows. If we have some point y in the image under the mapping F, and we have some preimages, so these preimages may not to converge to some boundary point, some cluster point. This situation is excluded for discrete mappings. It is known that quasi-regular mappings are open and discrete. Also, Stoilov has proved this, that analytical functions that we study in the university also are open and discrete, excluded the situation when the analytic function is a constant. Here we recall some notion that is called the Hordal metric. The Hordal metric between points x and y, where we can see on the picture here, is the Euclidean distance between projections of these points onto the Riemannian sphere. It may be shown that the Hordal distance may be calculated directly by this formula. Some notion about the generalization of the BMO class, BMO John Nirenberg class, has a localization which was introduced by my teacher Ryazanov with his pupil Ignatiev in 2002 year. We say that a function phi has a finite mean oscillation at x0 if the relation 9 holds where phi epsilon dashed is defined by 10. So 9 and 10 is some analog of dispersion from probability theory, but there are no the square in this formula under the integral. This is dispersion without of the square in degree. Also, we use the notion Qy0, which is defined for a given function cubic by the equality 11. This is the integral average under the sphere centered at y0 of the radius r of the function q big. Let us give the following definition of the class which will be considered below. Given a continuum E in D and a number delta bigger than 0 and a Lebesgue measurable function Q, we denote by Fe delta the family of all open discrete mappings from D satisfying the above relation 5, 6. In other words, satisfying inverse Poletsky inequality for Q big at any point y0 from the closure of Rn, where Rn dashed is the one-point compactification of Rn, such that the Hordal distance of the imaged of the mapped continuum E more or equal than delta. Then the following statement holds. Let D be domain Rn and let the ball centered at x0 of the radius epsilon 1 is a subset of D for some epsilon 1 bigger than 0. Assume that Q is integrable, and in addition, one of the following conditions hold. Either Q in the FIMO class, or the relation 12 holds for some delta bigger than 0. Then there is R naught bigger than 0, which is that does not depend on F, such that the image of the ball contains in itself the Hordal ball centered at F from X naught of the radius R naught. So for Koebe theorem, we have the usual ball. Here we have Hordal ball, but this situation may be explained by the situation where F from X naught maybe tends to infinity under the class F frac E delta. Also, in the Koebe theorem, the radius R naught is equals to 1, 4, but here we don't know the precise quantity for R naught. We only say that this R naught exists, but we don't know the precise quantity for R naught in this theorem. Observe that the condition FIMO mentioned above and also the condition 12 may be defined at the point infinity with the help of the inversion. Y divide Y by the modulus in2 is the inversion with respect to the unit sphere. This result was published in journal Analysis and Mathematical Physics, which has the first quarter in this year. Thank you very much. It's over.
Thank you, Evgeny, for your presentation.